intro to navigation. Now, remember, during some of the first lectures, I mentioned to you that in robotics, navigation is not the act of moving from one place to another one. It's the act of finding out where you are in the generalized sense. So actually, in its most abstract form, or in the most demanding case, you should be able to find 12 variables: the position of the center of mass of the robot, the velocity of the center of mass, the orientation, and the rate of rotation. Okay. Most of the time I will focusing on motions in 2D, so we are not going to require to measure all those variables, but let's start nice and easy. So suppose you have a simple example. Well, you see on your phone, you certainly have a rate gyro. You have a rate gyro and something like a compass. So and I'm talking about motions about one axis. So if you move on the 2D plane and want to find out how the vehicle is rotating, then you have to put some sensors there. And two crucial sensors are rate gyros and compass and accelerometers. But let's simplify. So assume that you have a very good compass that gives you the north. I'm not going to get into the specifics, whether it is magnetic or geographic north or whatever. And then you have at least one rate gyro that measures the rate of rotation about a vertical axis. So suppose you have these two units, you purchase them somewhere. And you want out of these two units to build up a simple system that should give you very good estimates, not only of the heading angle and the rate of gyration, the yaw rate. Now you may comment, why do I need to do this? I already have the units. Yeah, but you have to pay into attention that when you buy some of these units, they are not very good overall the envelope of operation. So normally rate gyros are very good at what we call higher frequencies, and compasses are good at lower frequencies. So you want to mingle, you want to fuse the information so that you can get better estimates of heading and heading rate across a large range of maneuvers. So I'm going to assume that you have a compass. So I don't know, something like this, compass. And I have a rate gyro that measures speed rotation about the z-axis. So rate gyro. So you have one unit here, you have another unit there, you have a computer or some microcontroller, you read the data, you put the stuff together. Now, how can you come up with very good estimates of rate of rotation and heading based on the measurements given by these two units? So this is the simplest example of a navigation system. Shouldn't even call it navigation. I mean, navigation in the sense that we aim to estimate these two variables here. Every time you want to design a system like this, you in the back of your mind, you have to think about the physics. And what do you know? I mean, conceptually, don't think about the noise on anything. So if you have rate of rotation called R and heading angle called psi, what do we know? We know that derivative with respect to time of psi is equal to R, which means that psi is the integral of R. Okay, that's what you have there. And I'll leave that little bubble there for the reason that will become clear. Now, the measurements, when you measure this, so this is the model. This is conceptual. So integral compass or yaw is the integral of yaw rate. Okay, that's out there. Now, in practice, you are not going to be able to measure R and psi. You are going to have measurements, and sometimes we denote by measurements and measurements. And these are corrupted by a couple of things, but also by noise. And without being very rigorous, I'm also going to state that they work. Oops. They work in different regions of frequency, so without being very rigorous. So what does this mean? I'm repeating whatever I said before. It means that the rate shadow normally is very good at high frequencies when you agitate a lot. And the compass is good at low frequencies when you do slow motions. So here is the situation where you would hope to find an algorithm that would somehow bring the two together and complement them so that across a full envelope of maneuvers in rotation, you could get some very good estimates of the angles. Now, something that is very important about, so the word behind all of this is sometimes called filtering theory. Filtering theory. So in filtering theory, when you have measurements of some variables, and then you wish to get better estimates of those same variables, and normally in filtering theory, the estimates that are cooked up inside your computer are denoted by hat. So you have R hat and psi hat. These are estimates. So remember, R and psi is the real deal. That's whatever the vehicle is doing, but you don't have access to this because you don't know what the reality is with infinite accuracy. And then you have the measurements RM and psi m. So these are very, very basic and simple concepts. You would like to estimate, to get very good estimates of these variables by processing the data that you acquire through your estimates. So how do you go about computing better estimates of R and psi? So in principle, by measuring R, and I'm not going to start writing RM all over the place, even though it should be. And suppose that by some magic, the estimate that you can, I have not told you yet how to put these things together. So suppose that by some passive magics, you actually have the estimate equal to the real deal. Now, this is a mysterious step. We'll see. So what happens? You could simply say the following. Well, I'm going to assume that DR is very good. It's already my estimate. And then when I integrate this, I get an estimate of psi. So in other words, the model that you use that is based on the physics of the system could be the model that you run on your computer. So this is a bit weird because then in principle, you not even need to measure psi, because if you have a very good measure of R, then by integrating following this model, you could get the psi. Now, obviously, this is not going to work for a number of reasons. So this is different from R. There's another thing that is going to mess up with this simple way of doing things, which is when you buy a rate gyros, there's a bias. So rate gyro, it has biases. What does this mean? And the bias can be caused by many things. So if you have a rate gyro that you put here and you are not rotating, or you think you are not rotating, the rate gyro is going to give you a rate of turn for many reasons. Remember, for example, that if you have an extremely good rate gyro, leaving aside other considerations, Earth is spinning, so it's rotating. So even though you don't perceive it, so there's going to be a bias. And then, of course, if you put the measurement and there's a bias there, the moment you integrate the bias, so a bias is a constant, let's say. So the moment you integrate, you are far off. So the estimate gets far off. So, oh. Sorry about this. Okay, so let's try something simple, okay? To prevent this thing from taking off. So this is this guy over here. I'm not assuming we have bias here at this point. And let me put this here. So let's suppose you reach the stage where you have an estimate of R, which I call R hat. I have not told you how to do this. And then you integrate and you call this the estimate. But you don't know if this estimate is good or not, right? So here you have R. And for the time being, I'm going to assume that you don't have any biases. So this is equal to and no noise. So that's Rm. Now, there's even if the measurement of R is perfect and is not corrupted with noise, the moment you kick this in, remember that this integral starts at a certain initial condition, and then it does something about its life. So if your vehicle starts from 0 and you actually initialize it at 0 and everything is perfect, then again, you would not need the compass. But that's not the case. So the thing is going to deviate. So comes a very important point, which is the following. If this thing starts drifting for some reason, because I did not guess the initial condition or because there are other disturbances here, what can I do? It comes a very important concept, which is the following. This is the filter that is running inside my computer. Now, I do measure the psi that, again, can be corrupted by noise and stuff like that. I subtract, okay? And then I do the following. If psi, the measurement, is exactly equal to the estimate, the error is 0 and I do nothing. If there is some discrepancy, then I get an error that I multiply by a certain k and I feed in there to try and correct what is going on. This is the most simple system of filter that you can come up with. In other words, you have what we call the prediction. So based on the measurements of R, you predict what the psi should be. But then you measure the actual psi, you measure the difference, and you correct. So this is the prediction. And this is the correction. Now, why will this work? Now, so I'm not considering noise at this point. So let's look at the error, which is psi minus psi hat, right? So if you compute the derivative, you get the derivative of psi, which is the reality, which is R minus. And now psi hat, you go here. Psi hat, yeah, well, no, sorry about this. Minus, so minus, and this you have R. So psi hat, yeah, so you are here. So you get R minus K times the error. Okay, plus the error. So error is the difference, and when I compute error dot is psi dot, which is R, psi dot, which, yeah. So psi dot derivative is equal to R minus. So you cancel these things and you get y dot equal to minus KE. And this implies that the limit when tends to infinity a V of t is equal to 0. So you can be certain that by using this scheme, then asymptotically you get the error between psi and psi dot going equal to 0. So even if you started off with the wrong foot without the proper initial condition or something, the error will go to 0. Actually, the estimate will go to psi. Now, let's pay attention to something that is interesting. I'm assuming for the time being that the measurement of R is not corrupted with noise, okay? All right, we will get there. But you are right, it should be, I'll go back to this exercise, doing it more carefully. Okay, now there's something very interesting because you see, this is a system now where you have measurements of psi, and I'm not calling psi m or whatever. You have measurements of R, and you have this system here that you have designed with K positive, and you get estimates of psi and estimates of R. Now, if you look, okay, now let's look carefully at two things. So again, without going into many details, I mean, this is truly psi m, but I'm assuming that the noise is not terribly high. And this is the measurement of R without much noise. But now there's an interesting question. So I have this scheme here where you grab your rate gyro, you grab your compass, you make these measurements without noise, go through the system, and you get estimates of psi and estimates of R. And the first question you do is the following, or you pose is the following. What is the relationship between psi and psi hat? So let's forget, you see, this is a linear system. So when you ask the question, what is this? This is caused by two things happening, the evolution of psi and the evolution of R. But because it's a linear system, the principle of superposition is valid and you can split them. So the first question is, and I am trying in a naive manner and in a very intuitive manner answer the following question. When I get measurements of psi and I get estimates of psi, what is the range of frequencies over which these measurements truly help me? So if you do some simple computations, and I'm not going to repeat this here, so you for example, if you go through this cycle and look at the relationship between psi and psi hat, you get that psi hat. I don't know if you are familiar with transfer functions and Laplace transforms. Okay, so if you compute this, then you get K over S plus K. This is very important because it tells you, oops, it tells you something very interesting. Your only degree of freedom in this design is K positive. And we know that the system is stable no matter what K is, as long as it is positive. Now, if you do the Bode plot of this transfer function, you get something like this. So log, 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 log. So at frequency 0, you get the gain of 1. So you get 0 dB. And then you get something like this. And then you get an asymptote. And then you get something like this. What this tells you is very important, is that using this estimator, you are relying on the measurement of psi to get an estimate of psi hat at the low frequencies. And in fact, you can actually state up to what frequency this is valid. This is K, radians per second. So why is this important? Because when the manufacturer gives you the compass, or if you do some experiments, you should have an idea as to, I'm not being very rigorous here, over which region of frequencies the compass is good, okay? And if the manufacturer, or you find out that the compass is very good, let's say up to 0.2 radians per second, then you should choose the K in your design to be approximately equal to 0.2. And then this means that you trust the information provided by the compass up to 0.2 radians per second. And now, whatever the manufacturer gives you and whatever you want to extract out of this system, they match each other. Okay, but there's something missing. What about the complementary frequencies? So I have looked at the transfer function from psi to psi dot. It doesn't make much sense to look now to compare things. I mean, if I ask the question, what about the rate shadow? How is it contributing to the good estimate of heading at higher frequencies? You could be tempted to look at the transfer function between R and psi dot. Okay, but this is a rate and this is an angle, so it's not going to work. But what you do is you invent a variable, which is the integral of R. So to some extent, it's an angle. And then you ask the question, what's the impact on psi hat? When you do this computation that I'm not going to do, you get the transfer function S over S plus K. And S over S plus K is very interesting because when you do the body plot, it gives you something like this. And this tells you that you are trusting the rate shadow at high frequency and the compass at low frequency. That's the beauty of this. How do you set the K? Like I said, you go to the characteristics of the equipment obtained from the manufacturer, and that's how we decide where K should be. There's another very interesting thing, because when you look at these transfer functions, and I'm going to call this one T1, and the other one that are here, T2, when you add them up, you get exactly 1. So this means the obvious, that if the measurements of R are perfect over a higher region of frequency, and if the measurements of psi are perfect over a low region of frequency, when you embed everything into this filter, by magic, when the platform moves, you are getting very precise estimates of the heading angle, because these guys are contributing in such a manner that the sum of their contributions is equal to 1. This is a very famous filter. It's called a complementary filter. And the reason why I started with this, it's because it's very easy for you, if you ever wish to read about estimation theory, filtering theory, so on and so forth, to start at a very high level, very abstract, and then at some point you lose sight of what is going on. So remember, it's very important not to lose track of the physics of the system. And this is a very cute filter called a complementary filter that, in fact, gives you a recipe for the choice of the gain K that you have there. So K is going to specify this break frequency, and that's how you choose it. So this is something that you can try with the rate shadow and the compass, and mingle the two things using this, and you'll see that it works very well. Now, if you look at that figure that I had before, then you can see that what you are implementing when you implement the code is simply psi dot. And now I'm going to put measurement plus K measurement minus psi. This is what you implement in practice. So you go here. I did not consider the noise and all that stuff in order not to complicate things. But now if you put Rm and Rm, you get the derivative of the estimate is the Rm plus K psi m minus psi m. So that's the cute first order complementary filter. It's the simplest thing that you can think of in order to fuse information from the rate gyro and from the compass. There's a very, very, very important detail here, which is the following. See, when you write this down, so let me copy here because this is important. Psi dot, this is psi dot, this is measurement, this is psi m, and then you get K. This is it, okay? Okay, there's a very important thing in filtering theory, because when you have sensors measuring stuff, you are essentially saying, well, these are measurements, which is true. But remember, you have two kinds of measurements here, the rate gyro, and then something that appears there at the output. And see where the rate gyro information appears at the input. This is an input. And this is crucial. That's what characterizes a complementary filter. And this basic concept that then I'll exploit in more detail paves the way for the development of a certain type of filters that are very important and that are very much linked with physical reality. So this is a simple example, fine. So now the big question is, all right, how do I work out more complicated cases? And here, let's start by writing this. So let me think about this. Yeah. Okay. Now, remember when we talked about the LQR regulator, then whenever we had a description of the system, we decided to describe it in terms of the state variable called X. Here we are doing to do exactly the same. So this is very trivial in this case, because if I ask you design a filter to bring together these two variables and produce some good estimates, whatever I wish. So remember, the first thing that should come to mind is what are the physics? And the physics are the derivative of psi is equal to R. We are ready. So in order to write this in a very uniform manner, I'm going to call this variable X. And R, I'm going to call U. So in this case, what do I have? The derivative of X is U, right? Okay. So the derivative of X and U. And what is it that I am interested in? I'm interested in the variable X. Why am I writing it in this manner? Because when people study filtering theory, they like to write in the form X dot equals something and then Y equal to something. And this Y is related to the state variables. In this case, I'm only interested in X. So that's it. So the big question is, when you have a system like this and you have measurements, what do you do? Okay, so remember this is R, and remember this is psi. And now I told you that the person that revolutionized the design of control systems at the time was Professor Kalman. And among many other things, he came up with a solution for the famous LQI problem. Remember this. But at the same time, he also came up with a beautiful way of designing filters or estimators or whatever, and other kinds of things, which is truly amazing. Now, notice that here, so far I have not included the noise explicitly, but under the veil of the framework of Professor Kalman, you'd write things in this manner: x dot equal to u, y equal to x, and then he sprayed some noise here. So this one is sort of obvious because it essentially says the following: when I look at y, that is psi. In fact, I cannot measure psi exactly. I have some added noise. So this is called measurement noise. And this one has to do with the input and the rate shadow and stuff. So it's called the state noise. This is a fundamental part of the theory. So Professor Kalman essentially assumed that when you look at the system and you have some things that you can measure and you want to estimate some variables, you can start by writing the system in this form, where on top you have the state noise, so it affects your state, and the measurement noise that affects your variables, your measurements. Now, to simplify things up, it is often assumed that eta S is a Gaussian process. Question, is this always the case? I mean, obviously not. But this is the way the theory goes through. So you have to be careful at some point. So it's characterized by zero average and then a certain standard deviation, right? So that's the state noise. And NM, which is the measurement process, it's characterized again by zero. And here I believe I use sigma M. Okay, so you have the state evolving, which is the angle psi is doing something. And it's evolving according to this relation. It's driven by the rate gyro. There's some noise associated with this. And then you can measure not the psi itself, but psi corrupted by measurement noise. And now the question is, what can you do in order to come up with a good estimate of x hat? And then if you can get a good estimate of x hat, which is the psi, then you get a good estimate of the rate of the rate of variation. But the most important thing is the heading. Okay. Now there's a bunch of theory involved in all this. What Professor Kalman solved was the following problem. There may be many ways of trying to solve this problem. So I have to bring some characteristics of optimality here. So Professor Kalman wrote it in such a way that what we wish is to minimize the expected value So in other words, what scheme should I conceive of such that, and this applies when t grows, when t goes to infinity, so that no matter what maneuver I perform, which is given by the heading, what scheme should I come up with such that the estimate approaches the X with good precision, but because this is all corrupted by noise, Gaussian processes, you cannot simply say that you'd like for this to go to 0. You try to minimize the variance or the covariance of this thing that you have here, okay? So that's typical filtering theory. So what he indicated was a very clear method. And I'm just explaining for the simple case that I have here, but of course you can generalize to other cases. So to more complex cases even, given the system that is physics-based, given the characteristics of the noise, and given the fact that you want to do something to produce an estimate that will minimize this variance, how do you do this? So, and then essentially found out in a beautiful paper the following result. Now, in the case of the LQR, I also wrote down the solution for the LQR. Remember the Riccati equation, all that stuff. So what he wrote down was the following. In very general terms, if you have x dot equal to ax plus bu plus noise in the state, and this could even be a vector, and if you have y plus measurement, this is the more general form that includes the one you had before, then under certain assumptions, there's a structure, a filtering structure that actually minimizes this, let's call it the filtering error, that is given by the following. This is the solution. The estimate, what you do is the following. You start by copying your model, ax plus bu, you see? So this is your model, and the solution is, so instead of x, you have x hat. You start by copying this. So if there was no error, if there was no noise, and everything were perfect, then by sending the measurements of u through this thing, and if you start at the initial, at the correct value, then you'd recover x exactly, but that's not the case. So you have to compensate as we did before in the simple case. So the way you compensate, how do you decide when you have to compensate or correct? Is when you go at the output, which in our case is the heading, you multiply by the estimate. So in this case, in our case, this is simply psi minus psi hat, and you put the gain here. So this magic K, and again, he showed how to compute this K. In fact, I think he calls it L, but I'm calling it K. Now we have gone through a simple case where this case is where this K is a scalar, but it could be a vector. Now look at the beauty of this. It tells you the following. The best estimate in that sense is obtained first by doing what we call a prediction. So if you have your model, you have your U, and then you predict forward. You are going to start drifting for a number of reasons, and then you have to start correcting. How do you detect that something is going wrong? It's when there is a discrepancy between the true measurement and the predicted measurement. And then you compensate by multiplying by a matrix gain. So in our case, you have x dot, which is psi dot, equal to u plus state, and then you have y, which is the compass plus an m, which means that a is equal to 0, b is equal to 1, and c is equal to 1. And from here you got immediately x dot equal to u plus k y minus x, which is what we had before. Okay, Now, don't let yourself be deceived by the apparent simplicity of all this. I mean, for the case that I went through, the important thing to bear in mind is you do a prediction. So based on your knowledge of the model, and if you go through the U and you fit it, and you close your eyes and keep propagating, something will go wrong because of noise or whatever. And then you have the correction term. So this is the correction. So when you interact with someone, if you know that person, if you think you know that person very well, the way you address that person or so ever, you build the model of how that person behaves in relationship to others, and that's how you act towards that person. If you detect that something is going wrong, so you are sort of predicting the behavior of the person and acting accordingly. If something starts going wrong, it's because there's a deviation between the behavior that you predicted of that person and the real behavior. You have to correct your strategy. So that's exactly the same thing here. I mean, this is a bit, the equivalent thing is a bit ridiculous. Just wanted to give you some idea. Now, it is now the catch, not the catch, the very important thing. When you are in a very general setup, and I'll show it to you, where instead of a single scalar, you have a vector, you have a matrix, you can have a system with many inputs and many states and many output variables. When you have all this, how do you actually find the K? And again, Professor Kalman gives us a way of computing the K by solving another Riccati equation. So you solve another Riccati equation, which is very interesting. It's a different Riccati equation. Okay. So I'm not going to get into this, but let me tell you something very, very, very interesting. For the specific example that I'm giving you, which is this one, what would you suspect? That this K should depend on the intensity, in other words, the variance or covariance of the state noise, the process noise and the measurement noise. So what I'm going to tell you applies to the very specific example of a scalar, but then you can extrapolate it to far more complex systems, and whatever comes out of it is quite beautiful. In this particular case, the value of K depends on the ratio over sigma m. It only depends on this ratio, okay? And now that's where the intuition comes into play, and it's very, very important to bear this in mind when you do the design of an even more complex filter. If sigma m tends to 0, this means that when you are measuring EO, you are measuring it with very, very high precision, or with very good precision. And it turns out from the equations and the Riccati equation and all that stuff, that when sigma m is very small, or when this ratio is very large, this value of K increases. And this is very important because it tells you what now is obvious. And now this is a crucial part. If you are trying to estimate a certain variable, and you are relying on measurements of a sensor, and the sensor is corrupted by noise that is extremely small, you can trust that sensor a lot. And if you can trust that sensor a lot, this means that you can stretch the frequencies up to which you can trust your measurement. Remember, this is K. So if a manufacturer tells you, look, I have this sensor here. Let me go back into. I'll get back to this. On the other hand, if sigma m is large, then you have to. This thing goes down, and you have to recoil in the frequency, and that's how we play the game. So in practice, in order to find the K for a more complex case, whatever I'm going to say is not the recipe, but conceivably you could even set the covariance of this guy equal to something, identity, and then play with sigma m up and down, and then you'll see that your filter will start reacting more or less to the sensor over a desired region of frequencies. Now, when you study filtering theory, you don't learn it this way, because people are going to tell you the K is whatever is related to the covariances of these two guys here. And the question is, what is this covariance? Who's going to tell you the covariance? Well, certainly when you buy one of these sensors from a manufacturer, more than likely he is not going to tell you what his covariances are. Okay, so there are two ways of talking here. The classical way of looking at this, and by taking as sacred some form of covariances, and then you have to find them through measurements, or in other applications, aerospace, you have to find them. Here, what I'm telling you is that in many applications, these covariances are not true covariances, and they play the role of tuning knobs so that you can choose the bandwidth of your filter. That's it. And this is extremely useful. Okay. So for example, if you have a filter running to estimate some variable, and you notice that the speed at which you can estimate that variable is very low speed. So what you do is you go to the sensor that is related to that variable, you decrease the covariance, and boom, it starts getting you faster estimates. But then you could say, well, what if I truly have some knowledge of the covariances? That's another story. Okay. So in general, and I'm taking far more time here than I had anticipated. So in general, well, I told you what it is in general. So let's now go back to the case of the rate gyro and the heading. But now suppose you have some bias in the measurement of the rate gyro, right? So you have so there's bias. In the right gyro. So this system is not going to work nicely now. So this is the system. That is the psi. This is equal to x1. Because now when you measure R here through Rm, and I'm not even considering the noise, there's going to be a bias. So when you have here R measurement is R plus bias. And if you have a bias here, it's going to drift this integrator and you will be lost. So the big question is, what do you do now? Okay, now you do a flip and think of what we did for the LQR. And you remember very well that when we wanted to reject a certain constant disturbance at one point, you put an integrator before. You do exactly the same trick here. So you put an integrator here, and you call the output psi. And I've not told you what the filter will look like, in the hopes that at some point, remember what we did for LQR, the value of this will kill exactly the bias with a negative sign. So this is beautiful because the set of tricks that you have used for LQR, you can sort of bring them into the realm of filtering theory using other tricks. Now the question is, all right, but now this is more complicated. So what do I do? How do I design the filter? Well, you do the following. So you have x1 equal to psi and x2 equal to this variable. This is a virtual variable. It's an artificial variable, right? Now, if you put all these together on top of each other, you get x1 dot, x2 dot equal to. So you got to get derivative of psi. Derivative of psi is equal to psi, is equal to c. So you get 0, 1. And then you get whatever was out there. Plus 1, 0. And this is the u that in fact is the Rm. The derivative of this guy here, the derivative of this guy, when you insert here, because there's nothing here, the derivative is 0. This is a very, very common trick. The derivative is 0. In other words, you are assuming that the bias is not going to change. And then you put 0 here, and then following Kalman, you have eta S1, eta S2, and you have your system for which you wish to design. And then, of course, you have y is equal to x1, which is the heading measurement. So what Kalman tells you is that under certain circumstances, and given these covariances, the covariance of the measurement error, the solution will be estimate. You start by copying. So this is ax plus b, this is b, u. That's the prediction part. And now you subtract y minus the measurement, or no, yeah, y is the true minus, and multiply by k. That's what Kalman tells you. So now let's interpret this in a very intuitive manner. If you look at that equation, what we are doing is the following. So psi hat, this is measurement. This is our measurement. This is that strange variable hat. And now you are doing minus. You get K1 and you get K2. And that's how it works. So Kalman is essentially telling you propagate forward. That's the prediction phase. But now you have to include another element there that will learn the bias. And then you do the correction phase, and it will give you rules to estimate or to compute the K1 and K2. This is a very common filter that people use when you want to do things of this kind. So it's not terribly complicated. If you compute the transfer functions from psi m to psi hat, and then from the integral of r that I'm going to call eta to psi hat, you still get something similar. Now they are second order equations, but they will give you something like this. So this is a beautiful little naive filter that combines the information provided by the rate gyro and the compass and kills the bias on the rate gyro. So now even if when you sit the rate gyro, it's going to drift and exhibit the bias, this is going to kill it. Because doing the analogy with the LQR, it's going to learn, because the system is stable, it's going to learn the value that it should put there to kill the bias exactly without knowing it. So it's a very important thing. Now, why did I spend so much time with this? With this example? Because if you solve this example, then very quickly solve another problem, which is the following. If you have a boat, if you have a ship, and here you have the inertial reference system, so you have XY, YI, and you have the position of the center in inertial. And let me assume that the ship is allowing some maneuver and the side slip is very small, and therefore the velocity with respect to the fluid is always aligned with the main axis. So I'm going to put here VR. This stands for relative velocity with respect to the water. Okay. Now, why do I do this with respect to the water? This will be given to you by a Doppler. And there are two different, if you are at the surface and you want to use the Doppler, maybe it's a very costly solution. But you see, if you are at the surface and if the sea bottom is relatively far, when you have the Doppler shooting acoustic waves, you probably will not be able to reach the sea bottom. But what the Doppler does, you can switch to what they call waterlogged mode, where you insonify a certain area and the way the acoustic waves bounce off the particles in the water. So you can measure the relative velocity with respect to the water, but which is not the inertial velocity, because this would require you to shoot against the seabed. So, and this means that the true inertial velocity is obtained by compose this guy VR that you express in I, and that is simple to do, because if you have a Doppler here and the heading unit, you rotate it, then you have the velocity of the water in inertial, and this will give you the total velocity in inertial. I already mentioned this to you, right? So remember the video I showed you, the aircraft trying to land. So it's exactly the case. I mean, if you are flying in this direction, there's the runway, there's wind, which in this case, there's the water, and then it's going like that. All right. So now, suppose you want to find the position of the center of mass of this thing. You might as well say, well, okay, I mean, if I have GPS, I don't care about all these paraphernalia because I simply read off. But suppose you are in some environment where sometimes you don't have access to GPS temporarily, and then it comes back, or you want something more precise because the GPS, the rate of refreshment, sometimes it's not good enough. But what we know is that the total inertial velocity, which is this one, is equal to the one given by the Doppler plus the velocity of the current that I'm assuming is constant. So this is the Doppler. And this is what? This is derivative. This is the derivative of the position. Okay? We already talked about this before. So the derivative of the position is equal to the velocity in inertial. Now notice the similarity with psi dot equal to r. So you can think of P, even though it is a two-dimensional vector, but you can think of P as psi, And you can think this guy on the right as R. And you can think of the current as a bias that you are getting. It's not exactly a bias in the measurement, but it's something that is biasing the inertial velocity. So there's no wonder that when you go through the design, and this is a very practical problem, where you are in the water, you have the GPS that gives you now and then measurements of P. You have a Doppler that gives you velocity with respect to the water. You don't know the current. How do you come up with a filter that will do a good estimate of the position? And then, without further ado, I'm going for the solution because it's basically a carbon copy of what I had before. Now we are working in 2D, but that's fine. You can do this for each one of the dimensions. Okay, so you get this. You get the position X in inertial estimate. Now you get here PXI measurement given by the GPS minus, and then you get the relative the XI, and then you have to learn the current. You put another integrated here. Then you do this K1, you do this K2, and you are done. This guy will learn the velocity of the current automatically, and it will kill the component that comes there, so that you get very good estimates of the position of the boat. Now, pay attention to something very, very interesting. Suppose the GPS goes blank for some time. So when you detect that there are no measurements, you cut this. And in this case, what you are doing is simply propagating forward the prediction phase. In other words, if somehow you have learned the velocity at which you go, you propagate it forward, you integrate, and you get the position. So there's not much harm done if you lose the GPS now and then. If you start losing for extended periods of time, then you may be in trouble. So that's the beauty of this kind of filter, because it applies to a wide range of cases, and the reason behind is so much intuitive. Okay. So now I have to make a decision here because God, 1 hour and a half is gone. I still had some examples of navigation that I'll go through very quickly, and then I still wanted to talk a little bit about cooperative motion control. So we'll stop here because now I'm going to go to the slides, but please let me know. I know this was a bit fast for you. For some of you, it may be completely new. I just wanted to give you a glimpse of what is going on. And if you are more interested in getting into the details, then you have to study hard to understand what's going on. All right. So are there any questions at this point? Okay. Yeah.
So this error will go large.
When there is no GPS, you don't even look at the error because there's nothing to. Oh no, but wait a moment. When you don't have GPS, the first thing you do is to cut this.
It means I have to forcefully cut that.
Yeah, you don't set this to 0, you cut. And this means if you cut, nothing comes from here or from there. And see the beauty of it. If in the process you have learned at which inertial speed you go, and if you have learned already what the velocity of the current is, then you keep integrating this and you keep getting very good estimates of the position. So the prediction phase kicks in.
But the problem is when GPS fails.
If
GPS fails, I mean, there is no GPS signal. But the problem is, the sensor will give me the previous values stored there. So how I know that, okay, there is no frequency.
You have to have some logics in there. I mean, you know, more or less the velocity at which you go. And if over a certain period of time you see the values of the GPS frozen, it's because it's not working. Okay. So there's some logic involved. So these are some cute exercises that one can give to students to actually implement on a boat. I know you guys don't have a Doppler at this point, but Dopplers are becoming very cheap. I mean, there's this Doppler called water length. I don't remember the price, but I believe it's less than, it's still some money, but maybe I don't know. I don't know. I think it's under 10,000 euros. I'm not sure about that. Okay. But there are cheaper Dopplers out there.
Same thing cannot be done with the accelerometer. I mean, you integrate one more time, try to get it.
Okay. Now, when you have accelerometers of extremely good quality, you are done. I mean, you double integrate it over a certain interval of time and you don't get much drift. You really need to have very, very good inertial units at that point. They are outrageously expensive. So again, the accelerometers that you normally get, they are very good, reacting very fast, but over the long run, you cannot rely on them. No. It's out of the question. Okay. My belief, I may be wrong, that's my interpretation of things, is that in most cases when you buy, for example, an attitude and heading reference system, that brings 3 accelerometers, 3 rate shiners, and maybe a flat skate compass. You are using the accelerometers mostly to estimate the angles. Okay. Not, I mean, they will give you let's say an instantaneous value of acceleration, but I don't think I would trust that to propagate, to integrate twice forward. No. Okay. Okay, so let's stop a little bit. systems. Oh, I don't know what's happening here. All right. I don't know what's happening here. Okay. Okay, so the first example is exactly the one I mentioned to you, where you want to do your estimation from rate gyro and compass measurements. So you have your rate measurements and your measurements, and you get your estimates. So remember the structure. So here we are providing estimates of psi, of the heading angle. The measurement is the true rate plus the bias, so you have to kill it. So this means that in the design model, you have d psi dt equal to Rm plus mu, and mu, then you have to learn whatever it is. So that's the thing you have. And I already talked about this. Now, let me recall you that when you implement this filter, you have the prediction phase. So that's this, that's the prediction phase. It's going from here to there. And then you have the correction phase and also there. So that's what you have. When you write this in terms of the whatever is specified in filtering theory, then what you have is the derivative of psi is the measurement plus the bias plus some state noise. The bias, you don't know it. You need to estimate it. You assume it's constant. So you are going to say, oh, sorry, that the derivative is 0, and then you have some state noise. And the measurements are the measurements of psi corrupted by noise. So this is what we went through before. There are people that look at this differently, which is, you see, here, when you implement this, the rate gyro enters as an input, right? Okay. Whereas the measurement of yaw enters as a true measurement. And some people like to see the rate gyro measurements appear as true measurements. So they go through that thing more complicated. I personally don't like it. Where essentially say the design model is the derivative of psi is rate plus noise. That's an approximation you have to make. I'm going to assume that the rate is going to change very slowly. It's approximately 0, which is not the case. Then you have to learn the bias. And then you go for the measurements. You measure the compass and you measure whatever comes out of the rate gyro, which is R plus the bias plus eta 2. So the only thing I have done here is that instead of having the rate gyro information as an input, it's also appearing in the set of measurements at the output, let's say. And many people do this. Why is it that I do not appreciate this? Because now you have 3 state equations, you have 2 measurements, and when you implement the whole filter, it becomes, I don't know how to get rid of this. It will not change. Okay. No, it's still there, right? I don't know how to get rid of this. Oh, it's not, it only depends on that thing there. Okay. So the thing becomes complicated. Now you have 1, 2, 3, 4, 5, 6 games. There are arguments as to why it would be more appropriate to do it this way. I personally will never go in this direction. Okay, let's think of a more complicated and exciting case. So now suppose that you are on board a ship and you have a vehicle underwater. Yeah. Okay. And this vehicle underwater has a Doppler. So it's getting measurements of velocity with respect to the water or with respect to the seabed. And then also your measurements. Okay. Now, if this AV is here and the boat is up there, you could start by doing what people call dead reckoning. In other words, you use the information of the Doppler, you integrate and you compute the position, but again, you are going to have drift and stuff. So now, and then you have to correct. So how are you going to get an estimate of where you are or measurement of where you are? So the way this is done, or one of the ways it can be done, is the following. You have a GPS on board the ship. And then you have this fabulous unit that I mentioned to you, the ultrashot baseline, that is capable of measuring the relative position of the underwater vehicle with respect to the ship. So there are many ways you can do this. One way is the ship sends a signal, look, and the unit underwater is going to reply. Okay. And on board the ship, you have the ultrashot baseline unit that measures the relative vector, position vector. And then you can transmit that information down. So once you combine GPS data and you have the relative position of the AUV with respect to the ship, you have the inertial position of the AUV that you can communicate to the AUV using a communication system. This is a very, very important operational case, all right? So, and the question is, if you are on board the ship and you actually want to aid an underwater vehicle navigating by providing these position fixes, how can one do this? This is AUV borne. So in fact, the ultrashot baseline is not on top, it's on at the bottom on the AUV. So it's what people call the inverted ultrashot baseline. So if you imagine yourself riding this AUV, you can measure your velocity with respect to whatever current or the seabed. You can measure your angle. And you may have information about your relative, your absolute position, because the ship sends to you the absolute position. Using the ultrashot baseline, you have the relatives, you can compute your own absolute position. And then I'm not going to spend too much time with this, but this is the way it goes. I mean, the derivative of a position is velocity. I'm assuming we are shooting against the water current, so there's the input from the water, the input in the Doppler here, and then you have to estimate the velocity of the current. And this is basically the example I have shown you before. So it works like a charm, because if you have an AUV running, you are going to get information from the Doppler. Then you are going to estimate the velocity of the water. And then by getting these measurements from the support ship, you implement these complementary structures and you are done. So this is a scheme that people use a lot. Okay. Now, when you look at this, then the way you implement is, this is the way you implement your filter. And we have seen similar equations like before. And what's the underlying design model? Well, the derivative of the position is the velocity with respect to the water plus the velocity of the current, which I don't know. Velocity of the current, I don't know. I'm going to assume it's constant. So the derivative is 0. And then the measurement of position given by the ultrashot baseline and the GPS is given by this plus noise. So it's a very simple system to implement that is quite useful in practice. So that's the example number 2. Example number 3, it's slightly different. That's when you are on top and you have something or someone doing some kind of mission, and on board the ship you want to find out what the AUV is doing. So on board the ship you have the GPS, and now you have an ultrashot baseline on top on the ship. You interrogate, you reply, and you get the relative position of the target with respect to the ship. So we flipped. So in the previous case, everything was running, let's say, on board the AUV. Now the shift is towards the situation where on board the ship you want to find out what someone is doing underwater. But if you think about this, oops. Look that in this case there is no direct or indirect measurement of V, because the Doppler is on board the AUV, and I am not assuming that the AUV is going to transmit the velocity up there. So we are going to assume it's quasi-constant, and then you get something similar. The derivative of position is equal to velocity, then you have to learn something, then PM, and you go through the same design. And in this case, the velocity that you don't know, you are going to assume it varies very, very slowly, so that it's almost, the rate of variation is almost 0. And then you put a 0 there. It's a very common trick, and that's how you design a nice complementary filter for this case. All right. Now, suppose you want to be more sophisticated. So you are looking at the target that is underwater, and you want not only to estimate the position and the velocity, but also the yaw and yaw rate. This becomes a little bit more complicated, because now you have the derivative of position, okay? There's a certain, oops. We are assuming that the AUV is going at a certain forward speed that is approximately constant, okay? But in order to bring in the rotation matrix, you have the derivative of P is the rotation matrix times U, and that's what you have here. And you also want to estimate the rate of turn. So you are going to assume these are common tricks. You're going to assume it changes very slowly, it's almost 0. And then you have these measurements given by the Doppler and stuff like that. Not by the Doppler, by the ultrashot baseline and so on and so forth. Now, at this point, you get some complication, because this is a linear time varying system. You see psi is going to change with time. So I'm going to skip this. Don't want to get into this. So now we have a problem, because the solution sort of looks very much like the previous one. So you are estimating the U, which is the body fixed longitudinal speed. You are estimating psi, you are estimating R. But now the price that you pay, because it's a time varying system, is when you go through the filtering theory, the gains that you have here are going to change with time, and this will make it more complicated to implement. But I wanted to call your attention that there's another level of complexity if things start changing with time. And now an interesting thing. Suppose now you have a vehicle underwater and it's trying to approach a station that is fixed. And this vehicle is equipped with a Doppler, your measurements, and now you don't have GPS, you don't have ultrashot baseline, And all you can do is to measure the set of ranges to a beacon that is on that benthic station. And you know where the benthic station is. And you still would like to estimate the position of the AUV. Conceptually, it's not very different because you have here the derivative of the position of the vehicle is the velocity with respect to the water plus the velocity of the current plus the noise. The velocity of the current is approximately constant, so the derivative is 0. And now what is it that you can measure? You can measure the distance between the position of the AUV and a beacon that is on that station. Now, this introduces another layer of complexity because now you have a non-linear system and you have to resort to other kinds of filtering like extended Kalman filter, but see that it still keeps its simplicity, all right? So the way it is implemented is, it's basically the same. Derivative of position is velocity, Doppler, you learn the current, you measure the range to a beacon, but now the solution will give you these gains that are varying with time. So bear in mind that this complementary filtering structure is almost, I would say almost naive at first appearance, but there's so much that it can tell you. I mean, if you stick to the physics of the system, you can come up with beautiful designs for certain filtering problems that are not overly complex, okay? So, sorry for having done. You have any questions? No?
Measure one variable say position. So I need two sensors, one for position and one for
Velocity. They complement each other. Yeah. But then the basic difference compared with other filters is that the measurement of velocity is going to appear as an input, not as something as at the output. It's a measurement. But classical people say that all measurements appear at the output. And that's not the case with complementary filters. They appear at the input. Because it's the natural way of doing this. Derivative of position is velocity. It's an input. And then you measure the position in other. So that's why we call these complementary. Yeah.
filters come in the inner loops that you were talking about. Of the big control system.
So what is the big picture? So for example, so there are 3 layers here. So suppose you have an AUV and you want this AUV underwater to follow a certain path. So the path is given. We already know, without too much detail, how you can have an AUV follow a certain path, right? So first you have to find where you are with respect to that path, and then you have to maneuver and stuff like that. So the problem is, how do you find where that AUV is with respect to the path? You have to find out where the AUV is in inertial coordinates. This is what that system will give you. It will give you the position of the AUV in inertia. Once the AUV acquires this information, it passes it to the path following control system. Then in its simplest mode is going to decide what speed or heading to recruit to approach. So you are essentially declaring now, based on what I know about the position of the vehicle, based on what I know where the path is, I'm telling, for example, if the speed is constant, the yaw angle to go through a certain motion. You give this to the inner loops. That will make sure that the heading angle will actually match very well the reference. So there's a 3-layer of things and everything has to work at the same time here, okay? All right. Okay, anything else? No? Okay. Okay, so now I really have to apologize because I'm going to do this relatively fast. The slides will be there. I just want to call your attention to this fantastic area of research. We talked a little bit about this, but okay. Oh, so what's happening here? Oh man. Okay, here we go. Okay, so this is the final set of slides. And like I said, I'll try to go fast. And please feel free. I mean, you have access to the videos and then to the notes. If you have any questions, please feel free to contact me. I'll be glad to reply and help you as best I can. So I already called you out. This was my first involvement in cooperative motion control. This was the Asimov project in 2000. And it had to do with the cooperative behavior of an underwater vehicle and a surface vehicle in order to have fast communications. So you can imagine a situation here where this vehicle is doing something and the other vehicle has to stay on top at all times. So they have to synchronize. They have to do some form of cooperation so that they keep establishing this communication link. So this is truly what we had in the proposal that went to the European Commission, where you have the underwater vehicle, the surface vehicle, ultra short baseline, so on and so forth. And it was a beautiful project. I mean, it's the first time that we exploited this. Did we get that far? Not really, because the systems were very bulky at the time. I mean, Dopplers, I remember we had a huge Doppler. Now we have a Doppler that fits in the palm of your hand. Embedded systems, they were not there at the time. And many other constraints, but we learned a lot in the process and moved forward. There are other reasons why you would wish to use cooperative motion control. That's one of the figures I showed to you when, for example, you want to sniff where these, let's call them smokes, are coming. So if you have a bunch of underwater vehicles, they are moving information, cooperation. Each one of them is equipped with a certain type of sensor for its specific kind of variable there. Then you could measure the gradient and do a motion along the gradient or upwards the gradient and eventually meet. It's easier said than done, but essentially go to the source. And I also showed you this project where we have the morph vehicle, and then essentially you have 1, 2, 3, 4, 5 vehicles working in cooperation, so they all have to talk to each other. So these are all examples of projects, and this one I mentioned to you, where you need cooperative motion control. Okay, you remember I showed you this picture and this even a video. So I think in order to start thinking about cooperative motion control, the easiest way is thinking about cooperative path following. So we already talked about path following for a simple vehicle, where you have a path and you have a vehicle. You can, for example, fix the speed and then maneuver the heading angle so that the vehicle converges to the path and flies along it. Okay, but now here is the situation where you want to do this with more than one vehicle, 3, 4, 5, 6, 10, or 20. And still, because we do not wish to complicate things at this point, let's assume that all of these vehicles are supposed to fly along paths that you know in advance. This can be changed. So in other words, you'd have, like for these vehicles to communicate, coordinate themselves in such a way that all of them would go along these paths with a certain formation pattern. They could go side to side, they could go under triangle or one after the other, so on and so forth. So this is called cooperative path following. So there's the path, there's the vehicle formation that you specify, speed assignment. In the case of straight lines, what you simply wish to do is for all of them to move at the same speed, which is not the case for more general paths. And then the fleet follows the paths and keeps desired formation patterns. The first reaction is, oh, come on, you have to give paths to each one of them. What is the application of this? Well, there are many applications. And in fact, you don't need to give the path to each one of them. You could give the path just to one of them. And then based on the formation, the vehicle has to try and deduct what path it should go through and even recruit the speed automatically. So you only do this for one of them. I'm not calling it the leader because there's no concept of leader in this approach. They talk to the neighbors and stuff like that. You can get into more complicated stuff, which is when you have a target that is moving and you have a bunch of vehicles that cooperate. And one of them, for example, has some sensor that tells it how far along the target is, tries to estimate the motion of the target, and then fits a path for the vehicles to follow. And I call this the cooperative target tracking. The motion unknown a priori, and vehicle formation, fixed target fleet distance, keeps a fixed distance from the target. There's also a very interesting maneuver. And this, again, this may sound very naive, but I'm going to give you an example where this maneuver is indispensable. So suppose you have, for example, 5, 6, 7, or 8 vehicles in the water, even at the surface before they start diving. And these vehicles, and I have experienced this, these vehicles come from different partners, right? And you are essentially saying, well, suppose I have 6 vehicles, I want them, they are scattered in the water. And I would like for them to start nicely in a formation, let's say 600 meters down there, and then they would dive synchronously, so on and so forth. You can't imagine the trouble that we had at the beginning, just cooperating, not the vehicles, but cooperating among humans to try and bring the vehicles into formation. Hey, speed this one. Oh, no, go to the lab. I mean, it would take forever. This is insane. So then we decided to come up with this cooperative go-to formation maneuver, where the vehicles are scattered after deployment. Then you can, of course, read off where they are. And you have desired initial formation patterns. That's where they should go to. They should get there at the same time with the same speed. And they should this maneuver, they should do this. Now pay attention to the word I have there. Spatially deconflicted trajectories. I learned this with the guys that work with aircraft, with formations of aircraft. It would be very difficult. For example, if you assign this vehicle to go there, this one to go there, and the other one to go there, I mean, intuitively, they are going to cross. And so if you don't want them to cross, the thing becomes very difficult. But if you say, well, I don't mind if the paths cross or the trajectories cross, no, the paths, but they don't collide in time, only in space. So they could end up doing something like this, you see, where in fact they collide, they collide apparently, but they don't because you avoid the collision. This is a very, very important maneuver. And the question is, how do you do this? So to give you a flavor, there's a whole body of literature on how to solve this problem at the conceptual level. That's called optimal trajectory tracking. So it's a beautiful problem. But most of these problems, you tell them, for example, I want these 3 vehicles to arrive there at the same time with the same speed. They cannot collide in time, even though you allow them to do this. And when you go through this process and you solve this problem, the computer will give you these trajectories. But trajectories are defined in space and time. So if these things are very tight, and one of the vehicles actually tends to cross the crossing point at almost the same time that the other guy is there, if there is some disturbance, you are in bad shape. So you have to flip it, turn this into, and there are ways of doing this, into a cooperative path following problem, whereby now you have to follow these paths with certain speed assignments, but they keep talking to each other so that they never collide. So it's a beautiful illustration of what we call cooperative motion control. This one is a little bit more complicated, but anyway. So how does one start looking into this? Fortunately, when we started looking into this, there was a whole body of literature, Murray and Sachs and Chad Babaya and many other people on cooperative control under communication constraints. Because the other important thing, if you want these vehicles to do these contrived maneuvers, like so, they have to talk to each other. And if one of them starts speeding up, the other one should lag behind, you know, things like that. But are you going to talk all the time? It's very expensive, especially when you are underwater. So let's be careful about this. You need to address the communication constraints. All right. So here is, so the problem of it should not be coordinated. Once I was giving a lecture in Norway, and I kept talking about coordinated path following or coordinated control. In a dear professor that I know there says, António, that is wrong. It should not be coordinated. It should be cooperative. So, what are you talking about? And she was absolutely right, because coordination, that's when there is someone to coordinate. There's almost a centralized scheme. Cooperative is when you have some form of, it's not decentralized, it's distributed, where each one is endowed with some form of intelligence. You talk to each other, so they coordinate themselves, they adjust to each other. So it should be cooperative path following. And again, I believe the first solution to this problem of cooperative path following came from two schools of thought at the time. We had been developing this in Lisbon with some success. But the theoretical setup was not at its prime yet. And at the same time, people in Norway at the TNU, Roger Skjetten, Thor Fossen and other people were also working along the same lines, but more advanced in terms of theoretical approach. And then eventually we converged. And the basic idea is very simple. It's what we call, so this is what we want to do. So in this case, three paths that are straight lines. You have three vehicles, and you want them to converge to the paths and then go along a formation, which in this case is side to side. So how do you do this? Well, let's look at two vehicles. So S normally denotes the length that the vehicle traversed along the path. So suppose you have one vehicle already on top of the path, the other one on top of the path, and this one has gone by S1 by S2, so the difference is S1 minus S2, right? So what is the solution? At the conceptual level, the solution is easy. Analytically, it becomes a little bit more complicated. You do what we call the divide to conquer approach, okay? So you have the different vehicles, you have many paths. Let's not get mixed up. Each vehicle runs its own path following algorithm to start with. So this one goes there, this other one goes there, that one goes there. So that's what you do. This is just an illustration. It's not exactly done in this manner. Now, once they are on the path or very close, they measure the coordination error, and then they decide, the vehicles talk to each other and adjust their speeds to coordinate. That's what you do. If one of them is far ahead, then it's going to find out and sort of slow down, and the other one is going to speed up. So the way we solve this problem is this divide to conquer approach, path following, coordination. Coordination on the top. This may seem very naive and even trivial. When you implement, it's not terribly difficult, but to actually show that what I have shown you is here is by assuming that the vehicles are already on the path, or it work if you start far away and you engage the coordination and you engage the dynamics and everything. How can you show that everything works well? That's the difficult part, but that's the analytical part. But from an implementation standpoint, it's almost trivial, all right? For the case of 2. The trick, as I mentioned to you before, is the following. So suppose you have these 2 straight lines, they are parallel, you have 2 vehicles, you have a path called gamma 1, and you have a path called gamma 2. That's the length along the path, length along that path. Now, in this case, we are saying that we are parameterizing the path by its length, okay? So we are not specifying, well, we are specifying the coordinates as a function of the length along the path. That's what we call parameterization. So the speed assignment for vehicle 1, you say, let me go at 1 meter per second. And then make the vehicle 2 keep up with vehicle number 1, all right? So in this case, it's obvious that the parameter that parameterizes the path is the length. And actually you declare victory when S1 minus S2 are exactly the same, when the error is 0. But if you see, a big deal is the parameterization of the paths. It may very well be that the length is not the correct way of doing this. In this case, it's trivial that it is. And the parameter that parameterizes these paths normally is called gamma. So in this case, it's trivial because you have 2 gammas. One of them is S1, the length along this path. The other one is S2, which is the length along the other path. So what is a good measure of coordination? That's when the difference between the gammas, error, oh, I can't, well, it doesn't say. That's when the error is equal to 0. My computer is not allowing me to see all of it. You can see that. Now, pay attention. When you tell these vehicles to go at a common speed, what essentially you are saying is make d gamma 1 dt, which happens to be ds I dt, equal to the speed of the other one, which is VL. And in fact, the speed should be equal because you want these guys to be equal. So the action is to drive this error to 0. So in this case, it's trivial. You want 2 vehicles to come from, I don't know where, converge to these paths. The paths are parameterized by the length because it's so simple in this case. Specify the speed for one and for the other one is exactly the same. So once they are on the paths conceptually, then you want to steer them so that the difference between the lengths is 0. Okay. The paths are not necessarily parameterized by the length. So suppose you want to do something that is the following. You want what we call a slant range formation. In other words, you have this path gamma 1, you have a path gamma 2, and you like for this vehicle to go at a certain speed that you specify, and you like for this vehicle to be at such a place that this triangle is formed, and this angle is pi over 4, pi over 4. okay? And then they should progress like this, always keeping this kind of formation. It's obvious in this case that if you have one vehicle here and the other one vehicle there, the length here is not equal to the length there. So if you want to reach this information by declaring that the lengths are equal, it's a lost case. So, but if you compute this S2 compared with S1, you'll see that it is the square root of 2S1. Okay? So then you move along. Remember, S2 is equal to the square root of 2S1. So what you do, because you want to declare victory when the gammas are equal, you redefine the parameters and you say, okay, for the path number 1, gamma 1 is the length, but for the path gamma 2 is 1 over the square root of 2S2. And now a good measure of coordination is to make the difference between the gammas equal to 0. So the action is to drive gamma 1 to 0. So when you make the two gammas equal, then you satisfy this constraint that you are here. So it's a very simple trick where you reparameterize the path so that you declare victory when the gammas are exactly the same. What about the speed assignments? Well, because you want the gammas equal, it's obvious that if you want d gamma 1 dt equal to something, and this you could do, for example, you could say for vehicle number 1, I want it to go at a certain speed, all right, VL. For the other one, in the gamma coordinates, the speed should be exactly the same. It does not mean that the inertial speed of this guy will be the same, because it has to go further away, all right? So the beautiful thing about this is if you parameterize the paths adequately in terms of the gamma, you declare victory when all the gammas are equal, and the speed in terms of rate of variation of gamma is the same for all of them. Okay, so what are the assigned speeds in the inertial coordinates now? Well, it's easy, because d gamma I dt is d gamma I dsi. So that's how the path parameter depends on the length and then the inertial speed. And this should be VL. So if you specify that ds1 dt is VL, ds2 dt is the square root of tvl. So naturally, if you make the gammas equal, when you assign a certain speed to this one, the other one will go at a higher speed, but you don't have to tell it in advance. You don't have to, okay? So the beautiful thing is that in the gamma coordinates, all speeds are equal. Things get a bit more complicated even. For example, if you want two vehicles and you want to go want for them to go along these two circumferences, all right? So if you want this vehicle to go shoulder to shoulder with that one, and you start here and you go back, and you start here and you go back, the lengths are not equal. So you cannot simply declare that you have reached victory when you have gone by the same length. It will not work. So you have to reparameterize the path again. In this case, it's not very complicated, because you can you can normalize by the complete length of the path. So what you do, see, what you do is the following. Define gamma 1, which is S1 divided by R1, and gamma 2 S2 divided by R2. So now the lengths of both circumferences are normalized by 2 pi. So if you go here by a certain amount, and this guy is aligned, it will go exactly by the same amount in the gamma 2 coordinates. So again, a good measure of coordination is the error, very small. And now make all the speeds in the gamma coordinates identical. So what are the assigned speeds in inertial coordinates? You do the computations. If the speed of this guy is equal to the speed of that guy and is equal to VL, when you go back to inertial, they scale by the radius. So this is the trick. it's the first trick in dual cooperative motion control. You want to do something with the vehicles to reach a certain formation. You have the paths, reparameterize the paths so that you meet your goals when the gammas are equal and they go exactly at the same speed. That's it. Okay. So there are other ways, but I'm not going. Time varying transformations are possible. So let's go back to the case. There's an interesting connection with multiple vehicle path planning. That's what I mentioned to you. See, this is the case where you do not allow the vehicles to intersect at all. It's called spatial deconfliction. But then I showed to you the case where you have temporal deconfliction. Dangerous spot. All right. Now, I'm going to skip this because it's not essential. So when you first look at the cooperative path following problem, you have to specify this path 1, 2, and n. And they could be anything. I mean, one of them could go up, the other one to the east, but you have to set the correspondence. When this vehicle is there, the other one should be there, and the other one should be there. So out of this, you parameterize the paths by the gamma coordinates. And because when you reach the desired formation, the gamma i's should be equal, you specify that the speeds of all the gamma i's are exactly the same, and maybe they are dependent on where you are along the path. So that's the basic thing that you start with. And that's why people say that you have converted the problem into the famous consensus problem. So consensus problem is when you have certain dynamical systems and you want sum of all the variables to reach exactly the same value or identical values. And this is what you want. You want for the gammas to be exactly equal and to go at a certain desired speed. That's cooperative path following. So when was this done for the first time? There was an int long ago in 1992 by Hinman and Hauser, where they were trying to they introduced some of the concepts, and then we redid this for the case of the project Asimov, cooperation between a top and an underwater vehicle. But the solution was very, very complicated. We essentially didn't know what we were doing at this time. And essentially it required one of the vehicles to know a lot about the state of the other vehicle or vehicles. If you stripline from the key concepts, this is the beautiful part. I mean, if, for example, if you have two vehicles, even with complex dynamics, and you want to do cooperative motion control, imagine that you are already on the paths. Each vehicle does not need to know about the complexity of the dynamics of the other one. All that the vehicle needs to know is how far along, as measured in terms of gamma, has that vehicle gone along the path. So you send away the complexity of the dynamics, which is quite beautiful. And then there was these advances like the group back home, and then Skjetten, Ile, and Torfossen, and also Michael Egerstedt. Now, the interesting thing is that in the solutions that came up, and even in a lot of work on consensus theory at the time, now it has changed completely, it was essentially assumed that the vehicles were communicating at all times to try and synchronize. And this was adequate, because when you are underwater and you have to communicate using acoustics, you cannot spend too much energy. It's costly and it's not easy. Okay, so communications are very important. So here is now the fundamental stuff that allowed people to do a breakthrough, which is to look at this consensus theory or cooperative systems. And if you look at the original work of Murray, Francis, and Jad Babaye, they looked at how did they address the constraints on communication? So I'm imagining that the vehicles are part of a graph, sort of a network. So this is one vehicle, another vehicle, another vehicle. Sometimes they call them agents. And here you have what we call bidirectional links. So if this one talks to that one talks to that one. And here you have non-directional links. This is what people call undirected graphs. And here you have directed graphs. So out of this came, there were some results that were known in terms of spectral graph theory that are absolutely amazing and very elegant. And this was the touch point. I mean, the key point in pushing through the communications and stuff like that. Now, when you look at communication constraints, you have delays. The vehicles communicate with each other with delays. You may have temporary loss of communications, so you don't know when the communications are going to fail. Sometimes this topology may change. Sometimes for some period of time, vehicle one may be talking to two, and then it cannot talk, and then later it will talk, and then there are asynchronous communications as well. All right. So when you look at these communications graphs, formally you have a graph that has nodes. That's what you see there. And the edges or the arcs, that's what's connecting the nodes. So a graph, nodes, and edges. Now, the nodes A and IJ are adjacent if there is an edge between them, so they can actually communicate with each other. And then you have a path of length R between node I and node J. There's a definition for this. The very important concept that the graph is connected whenever given any two nodes, there's a path between any two nodes of the graph. So it's called a connected graph. Now, Ni is the set of vehicles that vehicle I communicates with. They are called a set of neighbors, because you don't want each vehicle to talk with all the other vehicles, maybe just to some of the neighbors. And then there's a beautiful concept called the adjacency matrix of a graph. It's a square matrix where it essentially tells you what vehicles communicate with other vehicles. So Ni is the set of vehicles that vehicle I communicates with. And then there's the degree matrix of a graph where for each vehicle, it tells you how many neighbors it communicates with. And then finally, given these two, you can cook the very, very important concept of the Laplacian of a graph. Okay, now let me show you. So suppose you have this network topology. So vehicles 1 and 2 communicate, vehicles 2 and 3 communicate. All right. So 1 communicates with 2. 1 communicates with 2. 2 communicates with 1 and with 3, and 3 communicates with 2. That's the adjacency matrix. And then the degree matrix tells you that V1 only has 1 neighbor, V2 has 2 neighbors, V3 has 1 neighbor. So when you put this on together with a Laplacian, you get this thing called a Laplacian. The Laplacian is very interesting because when you pick up the Laplacian and put 1, 1, 1, you get 0, 0, 0. Okay. I don't know very well the story of what went on, but you see, this is, I'm not going to be very rigorous here. So this sort of tells you that if you want to find out if a vector of 3 entities has exactly the same entries, and then if you apply the Laplacian, if it gives you 0, that's the case. And this probably motivated something very interesting, because when L applied to a vector is 0, it means that the entries of that vector are equal. And this should remind you at this point, oh, what if I interpret this size as the gammas in my path following control system? So you see, it's very interesting. Why is this so? Because the way it was constructed, right? So you have one link there. So this is easy to see, there's no problem. Now, the interesting thing is when you apply the Laplacian to this vector, you get psi1 minus psi2, psi2 minus psi1 plus psi2 minus psi3, psi3 minus psi2. So this sets you thinking that maybe when I want to derive all the gammas equal to 0, and I want to use some very rich tools from algebraic graph theory, namely the Laplacian, this sort of motivates in a fuzzy way that probably one good way for the vehicles to talk to each other is for vehicle 1 to talk to vehicle 2. Vehicle 2 talks to 1 and 3 at the same time, and vehicle 3 talks to vehicle 2. So it's not clear at this point how this went on, but I believe this is at the genesis of what happened. There's another additional complexity that I'm not going to get into, which is when the communication links vary with time. So now we have to go for a divide to conquer approach. So you have to start with path following. And then once you are on the path, a long path coordination. This is only conceptual because the two coexist. Your vehicles are driven not only by the requirements to go to the paths, but to do synchronization as if they were on the paths. So they start interacting with each other. So you have to develop algorithms for cooperative path following, arbitrary dynamics, time varying topologies, so on and so forth. So this I mentioned already a little bit to you, given a geometric path and the speed assignment, then design a control law to make the position of the vehicle converge to a neighborhood of the path. And then with a certain speed assignment. So for each vehicle, you have the dynamics. It could be a simple ship with a rudder and with the yaw and the yaw rate, and then you measure the yaw angle, whatever. And the path following error, which just tells you how far away you are from that path. And the speed tracking error that tells you how far you are from the desired speed you want to achieve. Now, it turns out that if you look at the cooperative dynamics, they become very easy because for each vehicle, the rate of evolution of the gamma is equal to something you have to design, which is the reference, plus whatever comes from the path following algorithm, because you cannot eliminate this, because as you are doing cooperation, the vehicles are still trying to go through the paths. So you have this cross coupling here. Oops. Okay. So what do you do? And here comes the fundamental thing that people call the consensus law. So you have these vehicles. You want the gamma i's to be equal. And how do you do this? By adjusting the derivative of gamma i's. This is what you are going to design. And this is what comes from the path following disturbance. And inspired by what I told you about the Laplacian, people came up with the following control law, namely Varian-Sachs and Jadbabaya. When I have these vehicles flying, I'm going to tell each vehicle to move in such a way that the rate of evolution of gamma for vehicle I is equal to a desired nominal speed. And then I have the famous consensus law. Vehicle 1 talks to the neighbors. Vehicle 2 talks to the neighbors. Vehicle 3 talks to the neighbors. That's the famous consensus law that we use to do the cooperative path following control. All right. So when you do this, in compressed notation, this is what you get. This is your control law here. This is the nominal speed, and this you have to analyze further. Now, what is very interesting is that when the vehicles are progressing, you are telling the vehicles to adjust their speeds according to the Laplacian. Here is the Laplacian. Then there are gains that you have to design. This is the nominal speed, the feed-forward term, and this is the interference from path following. Okay, so in a nutshell, this is what we do when you have many vehicles doing the cooperative path following algorithm. You have to implement these sort of things. Now I'm going to skip this. What happens when you have communication losses? This is, I don't have time to get into this. Okay, now comes the big issue. Communication constraints. Do I need to communicate at all times? And when we first started working on this, it became apparent to us wrongly that probably you need to communicate a lot. And that to defeat the purpose of implementing this scheme, because I mean, how would you ever be able to implement it if you need to communicate so much, all right? So fortunately, there were some results around on network control, and these two papers were key by Yuk et al. And then Shu and Spania. And so this may look a bit complicated, but it is not. This is what happens when you have many vehicles operating. That's an agent. Each one of them is executing path following, but it's talking to the other ones, okay? There's a coordination controller, and there's a communication system that allows the vehicle to talk with the other vehicles. All right, now here is the trick. Let me give you the trick for the case of two vehicles. So you have these two vehicles, and you are running that algorithm where they are adjusting the gamma i's, and they are communicating at all times. You need to communicate at all times. So the trick is to put in a nice formal manner whatever I'm going to tell you. Each agent runs a model. So for example, vehicle 1 runs a model of what it thinks agent number 2 thinks of model of agent number 1. We talked about this once before. It's a bit twisting. Well, you know, Avanish has just gone through the process of implementing this, and in the end, it's almost trivial, the basic concept. So, and I gave you, I gave you, I don't remember what image I gave you. I think it was both people running in the forest or something like that. I don't remember. Yeah, you are on a forest, you are going along parallel paths, and you like, for some reason, I don't know why, to stay shoulder to shoulder. So we know the speeds that we wish, we go about doing path following, then we start communicating. You don't need to communicate at all times with the other person that you don't see. So what you do is, because you are assuming conceptually that you are already on the path, the models of the vehicles flying along the paths are very easy. Simple integrators, gamma I dot equal to something. So I run for example, you are running with me, I run a model of what I think you think I am doing. And then you do the dual thing. But I know exactly what I'm doing. So the moment this model starts varying from whatever I measure, and haha, I have to tell you that things change, and that's when I communicate. And this was key to saving communications. And we have implemented all these concepts. I think I have shown you. This is the very first time that we implemented this kind of controller in a simple manner with 3 vehicles that doing cooperation going along 3 circumferences. Okay. And then more recently, my student Hung completed his PhD, a beautiful PhD thesis, in which he put all of these things together. So path following, coordination, and what we call event-triggered communications, which is exactly what I told you about. Is this state of the art? I mean, we based ourselves on the work of many people. And I think the big virtue of Hung was to put everything together. And then, of course, he discovered some new stuff in the course of doing this and apply it to this specific problem of cooperative path following. And here you can see an example. Now, pay attention. At the beginning, the vehicles are communicating a lot because they are at different points along the path, so the models do not fit. But once they get reasonably synchronized, then they communicate less and less. You see here the communications. Until in the limit, if there are no disturbances, they don't need to communicate anymore, which is an extreme case because you are always going to have some noise. But it's beautiful because the amount of energy that you spare in or you save by employing these schemes is amazing. That's what you see there. So there are a number of interesting publications that you can come up with. So it's a very broad area. I mean, there's so much to do along in this area. But let me give you an example of something that Hung did, where he put together all of this stuff together with tracking a target underwater. So there's a target underwater. There are two vehicles at the surface. They can measure ranges to this target. And by measuring these ranges, they sort of know more or less where the target is. So then the trackers should move in such a way that they follow the target and at the same time use that information to run an estimation algorithm to improve the estimate of the target. And these are doing cooperative motion control using, in this case, it's simpler, but using the concepts I mentioned to you. So I think the results are beautiful because you can see here, this has all been implemented together with our friends from the University UNED in Madrid. So the sound is not there. So this is what you see when you go in the water. So you see, you have to go through all the steps of doing the theory, implementing the inner loop control laws, the guidance control laws, the path following control laws, cooperative control. And on top of this, you have to do the target estimation based on the ranges. There's a very interesting problem here, which is what is the optimal maneuvers of the trackers up there so that I maximize the information available for underwater target positioning. So this is very interesting because this is a situation, one solution is the target is moving and the other guys are encircling. This is done in an automatic manner, right? There you go. And this is the situation. There's another situation where you can get very good estimates of the target position by moving behind and measuring these ranges. All this is being done in cooperation. It's cooperative motion control, cooperative estimation, so on and so forth. So we are going to repeat these tests with more vehicles, and I'm very hopeful that things will work out nicely. So I'll leave you here. This was just a very brief introduction. There's an old field of literature out there on cooperative motion control, event-driven communications that waits to be explored. Okay. So that concludes it. Thank you very much for having had the patience of attending. I enjoyed teaching the course immensely. I learned a lot in the process in the sense that I'm always forced to understand things at a much deeper level when I want to explain them for the first time to someone that I know is not familiar at this point with the concepts. And that's the beautiful part of it. Okay. Okay. Thank you. Thank you, everyone. Okay.